Hello, everyone. I hope you're all doing well. Good day. Once again, this is Mary Jade C. Jakosalem, and I am currently a student enrolled at the AMA University Online Education. For this video, I will be discussing my course project for the subject ITE7104 or Data Communications and Networking. So to start with, let me first open the instructions in a Word file format that was given to us via our LMS. So let me open it. Okay, these are the instructions. So this activity aims to assess my knowledge and skills in applying LAN technologies and network services required by converged applications in a small scale or local network. So for the part 1 of this project, I am required to create a video presentation from the topics listed below. These are the topics. We have 3 groups of topics. I have to select one group of topics only. So the video must include an introduction, the discussion of the topic, and sample configurations using the Cisco Packet Tracer for each topic. The video should include me presenting the topics. For the visual content, the student may use different materials and style, example, PowerPoint, live discussion, paper discussion. I have take note that I have to make sure that my face is clearly seen on the video as well as a display on the screen. So for my course project, I actually decided to choose group 1. The topics include networking fundamentals, network types and topologies, and network models. So actually for this group of topics, there's only one sample configuration using the Cisco Packet Tracer, and that is for the different network types and topologies, which I will discuss later in the video. So as for my visual content, I have decided to use Canva, and actually my visual content is in the form of a PDF file. So to start with, let me open the visual presentation I made regarding the 3 topics I have chosen. So again, this is the visual presentation for the topic. So to start with, I would like to first do some reflections, because this is actually one of the last requirements for this subject. So first of all, I am very thankful to Prof. Maridel because I have learned a lot. The modules were really good. It's comprehensive, it's concise, it's really good. And I hope that you get something, you learn something from me as I am discussing my course project in this video. To start with, I will be covering 3 topics as what I've mentioned before. So there will be networking fundamentals, networking types and topologies, and network models. So under the networking fundamentals, we have different objectives for each topic. So for networking fundamentals, our main aim is to define computer networks. Second is to identify network components. Third is to identify standard representation for network devices. And fourth is to identify applications using the network. For our second topic, we have also 4 objectives. First is to discuss the 3 basic types of network, the LAN, the MAN, and the WAN. Second objective is to describe the server-client model. The third objective is to explain the network topologies, and the fourth objective is to identify network protocols and communication. And for our last topic on network models, we have also 4 objectives. First one is to differentiate protocol and reference model. Second is to define the TCP/IP model and OSI model. Third is to discuss the functions of the layers of the TCP/IP model and OSI model. And last one is to compare the OSI model with the TCP/IP model. So I guess we can start. So first, I will be discussing the networking fundamentals. So in this topic, in this chapter, we are expected to discuss what is networking, the different components of the network, all the basics, basically the basics in networking. So to start with, of course, we have to start with knowing what is a network, because a network is the central point of networking. So what is a computer network? So a computer network is actually a set of computers connected together for the purpose of sharing resources. Now, take note. Remember that the main purpose of a network is to share resources. So it can be in the form of sharing a printer, sharing files between different computers, sharing an internet access, and etc. Whatever resources that you wanted. So of course, from the sentence itself, set of computers, a network is of course composed of more than one computers. You cannot have a network if there's only one computer. So a set of computers, more than one, connected together, and its main purpose is sharing resources. Just like this one, a laptop, a tablet, a PC, they're all in the same network and they are sharing resources. So what are the components of a network? These are the basic components of a network. So actually we have two. So you have to always remember this. It's very simple. A network is always made up of end devices and intermediary devices. So what is an end device? An end device is a computing device that interconnects, has a unique IP address for every computing device. So first of all, they are different types of computing devices. And they interconnect because they're in a network. And always remember that end devices always have a unique IP address for every device. As what I've said in my previous activities, and think of an IP address as a given name. It's your name as a person. So it's imperative, it's essential that each end device has a different name so that you could actually, the network could actually distinguish them from one another. Furthermore, the end devices are either the source or the destination of the data that is being transmitted within the network. So it's either where the data come from or where the data will go. So that's also an end device. So some examples of end devices include a laptop, a smartphone, a tablet, a personal computer, a printer, an IP phone, so on and so forth. Okay, so actually, in the Cisco Packet Tracer, we can see the different end devices. So let me show the Cisco Packet Tracer to you. So this is our Cisco Packet Tracer. This is the user interface of our Cisco Packet Tracer. So just to show you, right here, we have different icons. And this one, the ones with the computer, the phones, are actually a list of end devices. So if you click this one, you will see here the various end devices in a network. So here we have a PC, a laptop, a server, a Meraki server, a network controller, a printer, an IP phone, a VoIP device, a phone, just a phone, a TV, a tablet, a smartphone, generic wireless, generic wired, and sniffer. So these are the end devices that can be found in our Cisco Packet Tracer. So moving on, going back to our PowerPoint. So those are end devices. Once again, they're computing devices that interconnect and they have a unique IP address. And again, remember, they can either be the source or the destination of the data being transmitted. Then we have the second one, the intermediary devices. For this one, they are the devices that provide connectivity to the network. They connect individual networks and connect segments within the same network. So basically, they are the devices that enables the connection in a network. Okay, so we actually have different types of intermediary devices. So we have four. So first, we have network access devices. Okay, so that's the first type. So what are network access devices? They're basically electronical devices that automatically connects a user to a preferred network. So these devices enable you to connect to a network. So some examples of network devices actually include switches, hubs, So these are examples of network access devices. Then you have the second one, the internet working devices. So internet working devices are any hardware in the network that connect different network resources. Okay, so one example of internet working devices is actually your router. So this is a router. I actually included some elements from Canva. This is a router. So that's one example of an internet working device. Third one is the communication servers and modems. So they're dedicated system to transfer files or ask information within the same network. So actually examples are from the name itself, servers and modems. Okay. Then the last one is the security devices. They're a system that monitors and controls incoming and outgoing network traffic based on predetermined security rules. So basically, they're used to secure your network. So they actually control what is going in and out of your network so that the data packets that goes in are actually safe and they don't have any viruses, malware, so on. So those are security devices. Think of them as like a security guard. They actually try to control what's going in and out. So one basic example, I believe you know this, is a firewall. So I believe most of our computers have firewalls. So firewalls actually determines what goes in and out, especially when you're using the internet. So to show you, in our Cisco Packet Tracer, we can also see the different intermediary devices. So right here, we have to click the network devices. So we have others, but network devices are your intermediary devices. So we have different types of network devices here in our Cisco Packet Tracer. We have here the routers. All of these are intermediary or network devices. We have routers. So we have here the different models of routers. We have switches. We also have different models of switches. We have here hubs. We have 3 models of hubs. We have here a wireless devices. We have here security devices like your firewalls, etc. And we have here the WAN emulation. So these are examples of your intermediary devices as found in the Cisco Packet Tracer. Okay, so going back, our next topic is about the different commonly used network devices. So it's very imperative that we actually familiarize ourselves with these devices because they can commonly be found in a network. Whatever the setup of network is, usually these devices are there. So the first one is an Ethernet hub, or just basically a hub. So this is an example. This is what a hub looks like. So it actually connects multiple computers together, making them act as a single segment. So that's an internet hub. So as what you can see here, they have different ports wherein you can connect for each port a different PC or a different end computing device. Then the second one is a switch or switches. So this one is an example of a switch. It connects devices together on a computer network. Now, actually, sometimes hubs and switches are commonly confused together. If you could see as well, they look very similar to each other. But what is the difference actually of a hub and a switch? So, a hub, actually, main difference is a hub, for example, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 12 computers connected to the hub. So when a data is being transmitted via a hub, that data is broadcasted to all the 12 end devices. So no matter what the data is, no matter where it is supposed to go, it will be, as long as it is broadcasted via a hub, it will be shown to all the end devices. However, the difference with a switch is that the data that is being sent will only be sent or accessed by the end device that is supposed to access it. So for example, I just want to send this information to computer 1. So only computer 1 can see what I sent. So that's the difference between a switch. But if it's a hub, if I sent something, all 12 computers will see the data. But if it's a switch, if I just wanted it to be viewed by computer 1, it will only be sent to computer 1. So that's the main difference. The third one is actually a router. So a router is routers are actually small electronic devices that join multiple computer networks together via wired or wireless connection. So this is what a router looks like. So I believe most of you have it in home rather, diba? Usually, if you have an internet connection at home, you can see routers because this is what enables you to connect, to have your Wi-Fi in your house. It's actually the router. And the routers are actually one of the most important parts of a network because a router is choosing the best path of where the data packets will go. So parang it's like a traffic controller. At the same time, it guides the data packets where they are supposed to be sent. So a router is very important. Fourth one is a network card. We also call them as the network interface cards or NIC. So this is what it looks like. It actually belongs to your PC. You connect this to your PC because it actually enables your device to connect with the network. So it's found in your laptops, in your PC, so on. And the last one is a modem. So this is what a modem looks like. Okay, so it's actually a device or a program that enables a computer to transmit data over. So basically, it brings internet service from internet service providers. So you need a modem for you to actually get an internet connection from your internet service providers, such as here in the Philippines, we have PLDT, we have Converge, we have Globe, so on. So the modem is the one that actually brings the internet service from the ISPs to your house. And usually the modem is connected to a router, or sometimes there are models wherein it's a router combined with a modem. So that's it. Then, these are the different representation of network devices or components as seen in our Cisco packet tracer. So it's very important for us to familiarize this as we eventually keep on using our Cisco packet tracer. So this is a router, a LAN switch, a LAN hub. This is a server, a desktop computer, a laptop, a firewall, an IP phone, a wireless access point, a wireless router, a WAN media, LAN media, and wireless media. Now, let's view them in our Cisco packet tracer. So here is our Cisco packet tracer. So right here, we have this is a PC, this is a laptop, this is a server. So as what you can see, it looks exactly the same here. Then we have your IP phone as well. Your IP phone is right here. Okay, so it's similar, right? It's the same, not similar. It's exactly the same. Okay, the IP phone. Then, of course, you also have here for your connections, for your media, this is a WAN media. You also have your LAN medias, wireless connection, so on and so forth. So, going back, these are found in our Cisco packet tracers as well. So these are symbols that we should familiarize ourselves with because eventually we are going to be using them from time to time. And the last topic actually for topic 1 is actually the applications that uses a network. So what are these? So first, games. I know that most of you are playing games, right? So if you are playing a multiplayer game between various devices, for example, Mobile Legends, COD, we are actually using a network. Without a network, we cannot play multiplayer games between various devices. If you could remember back then, when the internet was really not yet a thing, we have games. Like, for example, I can remember my brother used to play, like, what is it? Like, it's Dota, but it's not yet the connected ones. Parang Yeah, but yeah, I guess. But there's only like a single player, and even if you play multiplayer, you only have to use one device. So without a network, you cannot play with other players in different devices. So we need a network for that. So games. Number two are databases. It allows different computers to access the same database. For example, you can access the databases of Google because of a network. So if you search something, you're actually in Google, you're actually accessing their databases. An email. So of course, can you send email without a network? You cannot. Okay, so you can only send an email if there's a network. So a network allows you to send and receive emails. Video conferencing. So during the height of the pandemic, just like right now, I'm actually using Zoom to record this video, which is an example of a video conferencing application as well. So applications such as WebEx, FaceTime, and Skype is possible because of networks. Zoom as well is also a video conferencing app. Of course, if you have no internet connection, can you use the video conferencing apps? You cannot. So it's enabled because of a network. And the last one is a file transfer protocol, or FTP. Exchanging files over the web mainly uses network connection. Okay? So, for example, you wanted to send a file to your friend via Facebook, so it uses network. You wanted to upload something in Google Drive, it uses a network. And now for topic 2 on networking types and topologies. So, to start with, we have to discuss the different basic network types. Okay, there are actually 3 different basic network types. First one is what we call the LAN, or the local area network. So LANs are individual networks that usually spans a single geographical area, providing services and applications to people within a common organizational structure. So basically, one characteristic of a LAN is that it's usually used in a small area. Like for example, it's used in a computer shop. If you remember your internet cafes, in a computer laboratory, let's say in one school, wherein it's a small area. So we are using LAN for that. Actually, LAN is faster and more safer as compared to other network types. However, since it also has its limitations, such as the geographical area, the area that you are going to use it. So we are not using LAN most of the time. It actually depends on the situation. But out of all the network types, this is the safest and the fastest one, because it's a small area. So of course, relaying of information is definitely faster. For the next one, it's the Metropolitan Area Network, or the MAN. It usually interconnects a number of LANs using a high-capacity backbone technology and provides uplink services to ones, and the internet coverage can span between cities. Okay, so for this one, it's bigger than a LAN. It can span between cities. So it has a higher capacity. So it's the Metropolitan Area Network. It basically spans between cities. And the last one, and the largest geographical area, it can cover the largest geographical distance, is actually what we call the WAN, or the Wide Area Network. It's a network connection between 2 or more LAN, moreover a potentially large geographic distance. How large is it? We are talking about spanning it all around the globe. Hence, the picture here. Because a WAN can actually be used even if you are in France and your other end device is in the Philippines, a WAN is used. It's a gateway to handle communication between LAN and other networks. And of course, the most common basic example of a WAN is our internet. The internet is an example of a wide area network. So basically, the 3 is just characterized more on the geographical area that they cover. So the LAN is the smallest, followed by the MAN. A MAN is can be used within cities, but it also has its limits actually for the MAN. As far as I'm concerned, a MAN can span only 5 to 50 kilometers. But if it's more than that, we should be using the WAN, or the internet. Then, right here, I will be discussing the client-server model. So what is a client-server model? So it's a relationship between clients and servers. That's it. Very simple, right? It's a relationship between the client and the server. So we have to define what's a server, what's a client. So basically, servers, they have software installed that enables them to provide information and services to other hosts on the network or client. So this is an example of a server. So the servers are the ones that provide resources. Think of it as they are the givers. Okay. In this relationship, they are the givers. A client on this end is have software installed that enables them to request and display the information obtained from the server. The clients this time are the ones that request the resources. Again, the server, the one that gives the resources. The client is the one that requests the resources. So they are the takers. So that's like a give and take. So the servers are the givers, the clients are actually the takers. So usually the clients are actually us, the users. Okay, so that's a client-server model. Then we have here the different network design, or what we call topologies. Okay, so what is a topology or a network design or a network topology? So it's actually the arrangement of the computers in a network. So we actually arrange in a network. We are using different types of topologies because we arrange them depending on our needs, okay, and on the circumstances that surrounds it. So first one, we have the bus topology. So in this topology, every computer and network is connected to a single cable. So it's actually a topology used for local area network. So it's common, as what you can see. This looks like just like a typical internet cafe or computer lab setup. So if a cable is actually broken in this topology, if a cable is broken, then entire segment will fall apart. For example, this cable is broken. It's broken. Then the whole network goes down. So if we try to do it in our Cisco packet tracer, so let's do it. Okay. So this is our Cisco packet tracer. So actually, to save some time, I've already did it before I did the video so that the length of this video will be shorter. So let me open the file of the activity I made. Okay. Now, this one right here, this is actually from my lab activity 2. I just only revised some few things. This is an example of a bus topology. If you could see, they are all connected using a single wire. So if one connection here falls or fails rather, the whole network also shuts down. So, but this type of topology is actually used commonly in local area networks. So like for example, okay. So they are connected. So our printer here is connected to our laptops, to our PC, so on and so forth. So they belong to the same network. So I've just used here a switch to connect them all together. Okay. So the next one, the next topology. Let me go back to our file. The next topology is what we call the ring topology. So the ring topology, it actually forms a ring as each computer is connected to another computer with the last one connected with the first. So from the name itself, it looks like a ring. So the first one is actually connected to the last one. So it looks like this. Okay. So if you view that in our Cisco packet tracer, this is an example of a ring topology. As what you can see here, I actually formed a circle. So this is actually a ring. Okay. So if you can see, the end devices are also in the form of a ring because a ring is a circle, right? So the first computer is the first end device is connected to the last end device. So that's a ring topology. Then going back, The next topology is our star topology. So for the star topology, from the name itself, it looks like a star, but actually there are some cases wherein it does not look like a star at all. However, what is a star topology? All computers are connected as a single hub through a cable. So they are connected to, let's say, one switch, one hub. That's why it looks like this. There's as opposed to the bus topology, wherein if you have seen in our Cisco packet tracer, there are different numbers of switches and of hubs. This time, for the star topology, all end devices are connected to just one single hub. So if you see right here in our Cisco packet tracer, this one is a star topology. It looks like a star, right? Then all of the end devices are all connected in just one single switch. So for example, even if it looks like this, okay, so is this still a star topology? It does not look like a star at all. Yes, because once again, all the end devices are connected to one switch or hub. Hence, it's a star topology. If you can see here, the bus topology, there are more than one switches, switches or hubs, but for star topology, there's only one. And all of them are connected to that one switch or hub. That's a star topology. Then, part 1 is actually the mesh topology. So, in the mesh topology, all nodes cooperate to distribute data amongst each other. So, basically, all of them are interconnected with each other. So, that's why it looks like this. It looks like a mesh because all of the nodes are connected to each other. So, right here in our Cisco packet tracer, we have here an example of a mesh topology. If you actually look at it, this looks like a star. So for example, this switch is connected, this switch is connected to this one. It's also connected to this one. This one is also connected to this one. It's also connected to this one. And by virtue, this is also connected to this one via this switch. So it's all connected together. And of course, the end devices that are connected to the switch, in theory, they're also connected to all with each other. This switch, this connected to this switch, connected to this switch, connected to this, connected to this, connected to this. So they're basically connected to all the devices. So they are interconnected. Okay? Then the last one is actually the hybrid topology. So here, the hybrid topology, in this type of topology, you're basically combining two or more topologies in such a way that the resulting network does not exhibit one of the standard topologies. So, if you combine, let's say, if you combine a star topology and a ring topology, then that's now a hybrid topology. Or let's say you combine a bus topology with a mesh topology, that is a hybrid topology. The moment that you combine two or more topologies, it's already hybrid topology. So here, you can see here, like for example, this is actually a combination of different topologies. This one can be actually a star topology because it's connected to one switches. However, we have other connections, so it's hybrid. Okay, it's hybrid topology. Then, proceeding with our discussion, I will now discuss the different network protocols and communications. But before we delve into that, I want first to define what is a protocol and what are networking protocols. So basically, when we say protocols, they are rules. When we say protocol, they are rules, okay? A protocol is a rule that governs communications. It is made up of a group of related protocols that are necessary to communicate via electronic means. These are the rules that we observe when we are communicating electronically. So again, protocols are rules that govern communications. So what is now networking protocols? We are now getting more specific. They describe processes such as the format or structure of the message, how networking devices share information, how and when error system messages are passed between devices, and the setup and determination of data transfer session. So basically, they are describing rules on networking, such as how should a message be formatted or structured, how do network devices share information, when do error system messages occur, so on and so forth. So these are networking protocols. So these are some of the commonly used protocols in networking. First, I think at some point you have heard of this, the HTTP. Remember in your browser when you try to write in the space in your web browsers, like for example, www.google.com. Before that, you could say HTTP. Then www.google.com. HTTP actually stands for the Hypertext Transfer Protocol. It's actually the common protocol that governs interaction between web server and a web client. So again, a client is the one that requests resources, the server is the one that provides the resources requested by the client. So the HTTP is the protocol that governs this interaction. Okay, so for example, I wanted to search about Hello Kitty. So my request is Hello Kitty. So I am the client. I will be sending that request to the server. The server, in turn, will be sending out all contents about Hello Kitty. And that interaction is governed by the HTTP. Next is the Transmission Control Protocol, or TCP. So it handles the individual conversations between servers and clients. TCP also segregates the HTTP messages into smaller pieces called segments. So the TCP is the one that handles each conversation between a server and a client. And it is the one responsible in segregating the HTTP messages into smaller pieces called segments. So it's actually as well responsible for controlling the information exchange between a client and a server, such as examples, size of the data, flow control, how much is sent, how much is received, and so on and so forth. So that is a TCP, or Transmission Control Protocol. Third one is the Internet Work Protocol, or the IP. It's actually a protocol used by routers in selecting the best path to the destination host. So again, as what I've said before, a router is the one it's a networking device responsible for choosing the best path where the data packets will pass through. So the Internet Work Protocol is the one that governs that process. Okay? 4 is multiple protocols. So they're actually, again, similar to hybrid topology, multiple protocols, it's a message received by the host, usually containing multiple protocols. Because usually in the real life scenario, we are actually using multiple protocols in a single request. So that's it. That's multiple protocols. And then, the last one for our topic 2 is about encapsulation and decapsulation. So encapsulation is the process of taking data from one protocol and translating it to another protocol so data can continue across network. So in the encapsulation stage, you are taking one data from one protocol and then you translate it to another protocol. That's encapsulation. So since again, we have multiple protocols usually, so from HTTP, you translate it to TCP so that data can continue. So encapsulation means translating from one protocol to another. What about decapsulation? So from the name itself, it's actually the reverse or the inverse of the encapsulation process. So in an encapsulation process, we wrap the data. In a decapsulation process, we actually open the path. Because in the encapsulation, for example, we wrap the data so that it can actually be recognized by the next protocol. And then in the decapsulation, the next protocol is going to open the wrap. So that's a decapsulation. And of course, for our last topic, network models. Okay, so First, let us determine what is the difference between a protocol model and a reference model. So, a protocol model, from the name itself, it's quite obvious. It provides a model that is closely equivalent to the structure of a certain protocol. So, this type of model depends on a protocol. For example, HTTP, this model depends on HTTP, on TCP. So, this protocol model is modeled from a certain protocol. Meanwhile, a reference model provides a common reference for maintaining consistency within all types of network protocols and services. So, the reference model this time is not modeled exactly based on a protocol, but rather this is more standard. This model is, as much as possible, wants to be applicable to all types of scenarios so that it can actually maintain consistency. That's why it's a common reference for everyone. So that's a reference model. Then we have actually two types of network models. So what are network models? They're a set of network layers and how they interact. So basically, network models are made up of layers, and we are describing how each layer interact with each other. So first model is actually the OSI model. So the OSI stands for the Open Systems Interconnect. Actually, in this course, in ITE7104, we are going, the OSI model was really discussed in depth as compared to the TCP/IP model. So the focus actually was on the OSI model. So an OSI model is a system that breaks down network function. So it's the most popular type of inter-network reference model. So this one is an example of a reference model. So it consists actually of 7 layers. Don't worry, we will be discussing these layers in detail in the next slides. Then the second one is the TCP/IP model, or the Transmission Control Protocol or Internet Protocol model. So this is also known as the DoD, or the Department of Defense model. And this is the protocol used in the internet. And it has only 4 layers. The OSI model has 7 layers. The TCP/IP model has 4 layers. And it's actually a protocol model. So first, let's delve into the OSI model. So again, the OSI model has 7 layers. So we have here the application layer as the 7th layer. The 6th layer is the presentation. The 5th layer is the session layer. The 4th layer is the transport layer. The 3rd layer is the network. 2nd layer is data link. And the 1st layer is the physical layer. So the physical layer, the application layer, or the layer 7, is actually the topmost layer of the OSI model. As seen here in the picture, it's the topmost. So it provides a means for the user to interact with the software application. So this is actually the only layer wherein human-computer interaction takes place. This is the only layer where the user can interact with the network, for the network. So it's actually the application layer. Next one is the presentation layer, or layer 6. So in this layer, it actually provides proper common data format that is sent across application layer services. So for this layer, it's more concerned with data formats. So this is the presentation layer is concerned with the data formats. So actually, the presentation layer, correct me if I'm mistaken, but it's also called as the syntax layer. So that is the presentation layer. It's actually called again as the syntax layer because it is really concerned with the syntax of the commands, of the data format, so on. Meanwhile, the fifth layer is a session layer, the layer 5. This layer establishes, manages, and terminates connection between applications. And this layer actually provides services for our presentation layer. Again, the session layer provides services for the presentation layer. So this layer is more on the session. So usually sessions are done when there is a new request, and then this layer is more on whether managing those sessions, whether they will be continued or they will be terminated. So that's a session layer. The fourth layer is the transport layer, or the layer 4 in our OSI model. So this layer defines services to segment, transfer, and reassemble data, individual communications between the end devices. And again, this is really more on transferring of the data. And this layer is the one that describes how data is sent across the network. So it's really more on transfer of data. Now, the third one is the network layer, or the layer 3. It provides services to exchange the individual pieces of data over the network between identified network devices. So this is more on the exchange of the data. Exchange of data between one device to another. The second layer, or the layer 2, is the data link layer. This time, it provides methods for exchanging data over a common media. Example, your media is a copper wire. So the data link is more concerned on the media, on how you are exchanging media or exchanging data over a media. So we have different types of media, right? We have fiber optics, we have copper wire, so on and so forth. And the last one is the physical layer, or the layer 1. It describes the mechanical, electrical, functional, and procedural means to activate, maintain, and deactivate physical connections for bit transmission and to and from a network devices. So actually, this layer is really concerned with our physical devices in a network. It's concerned with the hardwares that is being used in our network. So that is our OSI model, the 7 layers of our OSI model. Next, I will be discussing the 4 layers in the TCP/IP model. So we have the application layer, the transport layer, the internet layer, and the network access layer. So first one, we have the layer 4, the application layer. So in this layer, it represents data to the user plus encoding and dialogue control. So this is also the only layer where the users can interact. So very similar to our application layer as well in our OSI model. Then, layer 3 is the transport layer. So this layer supports communication between diverse devices across diverse networks. Its main role, remember, is to transmit the data packets successfully. It's more on the transmission of your data over the network. Second one, that layer 2 is the internet layer. It determines the best part through the network. So it determines the best path where you will have to go through so that your data packets can actually reach their destination. So that is the internet layer. And then the internet layer is also concerned with how the data packets actually securely reaches their destination. And the layer 1 is the network access layer. It controls the hardware, devices, and media that make up the network. Again, very similar to our physical layer in OSI model. It is concerned with the hardware devices involved in a network. So here, we are actually comparing the OSI model with the TCP/IP model. So first of all, OSI lost out to TCP/IP as the protocol suite of the internet. So actually, that is why the TCP/IP is being used as the internet protocol, because OSI lost. So however, the TCP/IP model is actually mapped to the OSI model. And even though the TCP/IP is the protocol being used today by the internet, the OSI model is still often used to describe network communication. Hence, that is why the OSI model is the one that is being discussed in depth in our subject. So here, as what you can see, we are comparing them. OSI model has 7 layers, while the TCP/IP model only has 4 layers. However, they're actually, since the TCP/IP model is actually mapped out to the OSI model, so they have its equivalents. So as what you can see here, the application layer of the TCP/IP model is actually equivalent to the application, presentation, and session layer of the OSI model. In short, the three layers, layer 5 to 7 of OSI model is combined into just one layer in the TCP/IP model, which is the application layer. Then, the transport layer of the OSI model is equivalent to also the transport layer of the TCP/IP model. And the network layer of the OSI model is actually equivalent to the internet layer of the TCP/IP model. So, they have the same layer, but the layers only have a different name. So, in OSI model, it's network. In the TCP/IP model, it's the internet. And then, the layer 1 and layer 2 of the OSI model, the physical and data link layer, is actually combined to just one layer in the TCP/IP model, and that is the network access layer. Okay? So, that's it for my discussion for this project. I hope you really enjoyed. I was not able to show some Cisco packet tracer. I was only able to show one in the topologies because it's not actually applicable here in our lesson for topic 1 and topic 3. However, in conclusion, I have, again, just to review, I have discussed 3 topics. They are on networking basics, our network topologies, network models, and our networking types and topologies. So we have discussed about the different basic for the networking fundamentals. We have defined what's a computer network. We have discussed the components of a network. We have also discussed the commonly used network devices, at the same time the applications that uses a network. For our networking types and topologies, of course, we've discussed the different network types, the different network topologies, the client-server model, as well as the different protocols. So what's a protocol? We defined protocols, what are the commonly used protocols, and as well as encapsulation and decapsulation. For our third topic, we have discussed the network model. So we have discussed first the protocol and the reference model, as well as the two main network models, the OSI and the TCP/IP models. In this topic, we've also discussed the layers, the 7 layers of the OSI model and the 4 layers of the TCP/IP model. Lastly, we have compared the OSI model with the TCP/IP model. Okay. Now, I will be moving on to the remaining of the course project. Let me open again the Word file. So the part 2 of this course project is for me to actually answer the items here. So I have to complete the table. I have to convert the network address to binary, to convert the prefix length to subnet mask, and vice versa. I also have to identify the 3 types of addresses: network, broadcast, and gateway address. So here, we have some items here. So for item number 1, we're actually looking for the prefix length. So actually, the prefix length is based on the subnet mask. So that it's easier for me and faster to discuss it in the video, I've actually included already how to solve them. We are just going to fill out certain blanks so that it's easier for us. So again, in determining the prefix length, we need the subnet mask. So the subnet mask here is 255.255.255.224. Now, we have to convert the subnet mask into its binary form so that we know we can determine the prefix length. So actually, we all know that 255 is actually equivalent to 8 ones. 1, 1, 1, 1, 1, 1, 1, 1. But so that it's shown in the video, let us solve for it. So how do we solve for it? It's either we use a binary form only has 2 numbers, 0 and 1. So if we put 1 is basically for on and 0 is for off. So in trying to solve for the binary form, we actually have to deduct. So for example, our decimal here is 255. So the numbers here above are actually exponents of 2. So 2 raised to 0 is actually equal to 1. 2 raised to 1 is equal to 2. 2 raised to 2 is equal to 4. 2 raised to 3 is equal to 8. 2 raised to 4 is equal to 16. 2 raised to 5 is equal to 32. 2 raised to 6 is equal to 64. And 2 raised to 7 is equal to 128. Why do we have that? Because we have 8 bits and a byte. That's why we have 8 here. But we always start from 0. So that's why it's 0, 1, 2, 3 to 7. So here, our decimal is 255. So what we have to do is we have to ask ourselves a question. Is 255 greater than or equal to 128? If the answer is yes, we put here 1. So of course, you all know 255 is greater than 128. And then, what we have to do is we have to subtract 128 from 255. So I have here a calculator with me, so to guide me and to help me. So 255 minus 128. The remaining value is 127. Now, let's ask ourselves another question. Is 127 equal to or greater than 64? Yes, 127 is greater than 64. So again, our answer here is 1. Then we have to deduct 64 from 127. So 127 minus 64 is actually equal to 63. Is 63 greater than or equal to 32? Yes, it's greater than. So another 1. So then we have to deduct 32 from 63. So 63 minus 32 is equal to 31. Now, is 31 greater than or equal to 16? Yes. So another 1 here. Then 31 minus 16 is equal to 15. Is 15 greater than or equal to 8? Yes. Another 1. Then 15 minus 8 is equal to 7. Is 7 greater than or equal to 4? Another yes. So another 1 here. 7 minus 4 is equal to 3. Is 3 greater than or equal to 2? It's greater than 2. So another 1. Then 3 minus 2 is equal to 1. Is 1 greater than or equal to 1? 1 is equal to 1. So the answer here is 1. We only answer 0 if our value is less than the given here. For example, our value is 1. So, is 1 greater than or equal to 2? No. It's less than. So the answer here will be 0. So, again, as what I've said is if it's 255, 255 is actually equivalent to 8 ones. So, let me just copy paste it here. Since we have another 255 for the second octet. Then, another 255 for the third octet. And we have 224. So, let's solve for this. Okay. So, again, is 224 greater than or equal to 128? It's greater than. So, 1. 224 minus 128 is equal to 96. Is 96 greater than or equal to 64? It's greater than. So, another 1. 96 minus 64 is equal to 32. 32 is equal to 32. So, the answer is 1. 32 minus 32 is equal to 0, meaning the rest here will be 0. Then, hence, we have our subnet mask and binary. So, we have here 1, 2. So, we have here 8 ones. So, let me copy paste that one. And 1, 1, 1, and 5 zeros. So, our subnet mask and binary is 1, 1, 1, 1, 1, 1, 1, 1.11111111.11, so on and so forth, and 0.111000000. Then, this is now how we solve for the prefixing. I guess the music stopped already. Let me play it again. So that we have a background music. Okay, going back. So, here, how do we know the prefix length? So, actually, all you have to do is to count all the ones. Because a prefix length is actually the, wait. Yes, only have to count all the ones here because the prefix length is the number of ones in a binary subnet mask. So again, the prefix length is the number of the ones in a binary subnet mask. So here we have to count how many ones are there. So I know that we have 3 sets of 8 na 1. So that it will be easier for us, we just have to multiply 3 times 8 because 8, 8, 8. So 8 times 3 is actually 24. 24. And then 24 plus 3. 25, 26, 27. Hence, our prefix length is 27. So this is our answer for number 1. Next, for number 2, we're actually looking for the broadcast address. So, in order for us to compute the broadcast address, we need first to solve the number of host bits. So, actually, there's a lot of steps included here. So, how do we solve for the number of host bits? So, it's actually, since an IP address is actually 32 bits, right? It's a 32-bit address. So, an IP address is made up of 32 bits. So, hence, 32 minus the prefix length. So, our prefix length is actually 27. And then, hence, 32 minus 27 is actually equal to 5. Sorry. So, hence, our number of host bits is 5. Let me just double check that I'm still screen sharing. So, then, next step is for us to get the group size. Okay? So, the group size is actually 2 raised to the number of host bits. So, our host bits, it's 5. So, it's 2 raised to 5. So, 2 raised to 5 is, again, 0, 1, 2, 3, 4, 5. It's actually equal to 32. So, you just have to multiply 2 5 times. So, 2 times 2 times 2 times 2 times 2 is equal to 32. So, the concept of our exponents. Then, after which, we need the original IP address. So, our original IP address right here, it's here above, it's 172.201.95.32. Then, we have to get different network addresses. So our goal here is for our network address, our last derived network address to be greater, the value should be greater than the 4th octet. So this is the 1st octet, the 2nd, the 3rd, and the 4th. So here, we need a value, the 3rd network address should be greater than 32. So actually, the number of network address that you are deriving will depend on whether it is now greater than the value is now greater than the 4th octet, which is 32. So in this case, we just have first to copy the first 3 octets. So we just copy it, 172.201.95. So then for our first network address, we have to set the 4th octet to 0. So it's 0. So is 0 greater than 32? It's not. So we still have to proceed with the second network address. So again, we just copy paste the first 30 octets. And then 0 plus our group size. So our group size is 32. So 0 plus 32 is 32. That's our second network address. So, is 32 greater than 32? It's not. It's equal. So, we still have to derive one more network address. So, again, 32 plus another 32 is actually 64. So, we stop there because this time, 64, this time is greater than 32. Then, right here, the broadcast address this time is actually equal to 64 here minus 1. So we just have to minus 1 here. So our broadcast address is 172.201.95.63. That is our broadcast address. We deducted 1 from the 4th octet of our 3rd derived network address. So hence, the broadcast address is 172.201.95.63. Then for number 3. For number 3, we are required to solve for the subnet mask. So how do we do it? So for number 3, we need first the prefix length because again, it helps us determine the subnet mask. So our prefix length is actually 25. So here, for our subnet mask, hence our subnet mask and binary is 111111111111.111111.100000000. If you could see here, we have 25 ones. This is based on our prefix length. So for us to get the subnet mask, we have now this time to convert the binary form of our subnet mask into a decimal form. So again, I already encoded here the binary equivalent. So here we have 1, so on and so forth. So for us, for it to be easier, we all know that 8 ones is equivalent to 255. So let's just write here 255. But to be sure, how do we do it? We just actually add all the numbers here that has a 1 right here. So for example, 1. So since we all have 1s here, we have to add all the numbers here. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. It's actually equal to 255. So hence 255, 255, 255. Again, 8 ones is equivalent to 255. Now, for the last octet. So here, 128, we have here a 1. So 128 plus, we look for the other one. There's none. Hence, it's automatically 128. So, our subnet mask is actually 255.255.255.128. That's our subnet mask. Then, we proceed to number 4. So, for number 4, we are this time required to solve for the gateway address. So, if you could see here in our examples, there's a pattern. We just actually add +1 to the 4th octet in our gateway address. So we add 1 to our network address. For example, here our network address is 192.168.10.0. Our gateway address is 192.168.10.1. Same here, 32. We just basically copy-pasted the first 3 octets and add 1 to the 4th octet. So 32 here, this one is 33, 0, 1, 64, 65, 56, 57. So for this one, let's go back here. Our gateway address is actually, we just have to add 1 to our network address. So our network address is for number 4, our network address is 10.10.78.128. So again, it's 10.10.78.128. So it's actually +1, not minus. So, network address +1. Okay? So, 10.10.78.128 plus 1 is actually equal to 10.10.78.129. And that is our gateway address. Okay? And for number 5, this time, we are required to solve for the binary of our IP address. So our IP address right here is 192.84.235.0, which we have to convert to binary form. So here, 192, we have to convert this one to binary. So I have again included this table so it's easier for us. So here we have I've written the 4 octets, the 4 decimal form of our 4 octets, 192, 84, 235, and 0. So again, we just observe the same procedure. Is 192 greater than or equal to 128? It's greater than. So the answer here is 1. Then 192, we have to deduct 128. So 192 minus 128, it's equal to 64. 64 is equal to 64, so it's another 1. Then we have to deduct 64 minus 64, so it's equal to 0, meaning the rest of the numbers here will be 0. Now, let's move on to the second octet. 84 is less than 128, so it's a 0 because it's less than. 84 is greater than 64, so the answer here is 1. Since it's greater than. Then, we have to deduct 84 minus 64. The remaining value is 20. So, 20 is less than 32, so it's a 0 here. But 20 is greater than 16, so the value here is 1. Then 20 minus 16 is equal to 4. So 4 is less than 8, so another 0. Next, 4 is equal to 4, so it's 1. Then 4 minus 4 is equal to 0. So the rest here will be 0. And the last one, 235. Is 235 is greater than 128, so it's another 1. Remaining value is 107. I'm using a calculator. So 107 is greater than 64, so another 1. 107 minus 64 is equal to 43. 43 again is greater than 32, so another 1. Then we have to deduct 32 from 43. The answer is 11. So 11 is less than 16, so it's a 0. However, 11 is greater than 8, so for this column, it's a 1. Then 11 minus 8 is equal to 3. 3 is less than 4, so this one is a 0. However, 3 is greater than 2, so it's a 1 here. 3 minus 2 is equal to 1. So 1 is equal to 1, therefore it's a 1 here. Then the last value here is a 0, so everything is 0 automatically. Hence, the binary of our IP address is 11000000. 2 ones and 6 zeros. 1, 2, 3, 4, 5, 6. Okay, 6 zeros. 2, 4, 6. Then, 0.01010100. Then, 0.1110101. 0.8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Let me count to number 2, 4, 6, 8, 2, 4. So the binary of our IP address again is 11000000.010101011010101.0000000. It's quite long. So binary is long. This is our final answer for number 5. Next, for number 6, we are now again required to solve for the broadcast address. So for this one, we need our network address. So we have to first solve, we need to first solve for our number of host bits. So again, it's 32 minus prefix length. So if we double check, our prefix length is 24. Okay, so it's actually 24. So let's put it here. So it's gonna be, where am I? 32 minus 24. So 32 minus 24 is equal to, how much? 8. So our number of host bits is 8. Then 2 raised to 8. So next, we need to solve for the group size. So our group size again is 2 raised to the number of host bits. So it's going to be 2 raised to 8. So 2 raised to 8 is actually equal to, is actually equal to 256. Hence, our group size now is 256. Then we need our original IP address. Our original IP address is actually 192.84.235.0. So it's right here. So we need this one. Again, we just have to copy paste the first 3 octets and we're just going to make the changes on our 4th octet. So again, for the first network address, as usual, we put the 4th octet as 0. We set it to 0. So again, our goal here is that we should have, the 4th octet should have a number that is greater than the 4th octet of our original IP address. So our first network address is 192.84.235.0. However, the 4th octet is just equal to the 4th octet of our original IP address. So we have to create another one. So 192.84.235, then plus 0 plus our group size, which is 256, so meaning the value here is 256. Now, the 4th octet is obviously now greater than the 4th octet of our original IP address. Hence, we can now work on this. So we just have to copy this one. Then we just have to deduct 1. Just have to deduct 1 from our 4th octet so that we could solve for our IP, for our broadcast address. So, our broadcast address is now 192.84.235.255. So, this is our answer for number 6. Again, our answer for number 6, the broadcast address is equal to 192.84.235.255. Then, for number 7, we are actually required to solve for the prefix length. So again, for the prefix length, we need our subnet mask. So our subnet mask is actually equal to 255.255.255.192. And we have to get the subnet mask in binary form so that we could count the prefix length. So again, if it's 255, there automatically we have 8 ones. So let me just, we have 8 here. Okay. Then let us just solve now for 192. Again, same process. 192 is greater than 128. So the answer here is 1. Then 192 minus 128 is equal to 64. So 64 is equal to 64. The answer here is 1. Then 64 minus 64 is equal to 0, meaning the rest of these will be 0. Hence, our subnet mask in binary is actually 1, 2, 3, 4, 5. Okay, we have 3 sets of 8 ones. Okay. And then 1, 1. Okay, we have 6 zeros, correct. Okay. So now our subnet mask in binary is 111111111.111111.111111.11000000. All we have to do now is to count the number of 1. So here, the first 3 is actually equivalent to 24. Then we have 25, 26. So we have 26 ones. So in short, our prefix length is 26. Now, for number 8, we are now required to solve again for the broadcast address. So let's go. First, we have to solve for the number of host bits. So again, we have to deduct the prefix length to 32 bits. So the prefix length is actually 26. So we have to deduct it here. 32 minus 26 is equal to 6. Then, we have to solve for the group size. So group size is 2 raised to 6. And 2 raised to 6 is of course equal to 0, 1, 2, 3, 4, 5, 6 is equal to 64. So our group size is 64. Then we need the original IP address. Our original IP address is 172.99.184.64. Again, we just have to change the last octet. So first, for our first network address, automatically we have to set the 4th octet as 0. So since 0 is less than 64, we have to derive the second network address. So 0 plus our group size 64 is 172.99.184 plus 0.64. 64 is equal to 64, so it's not yet greater than. So we have to derive the third network address. So for the fourth octet, we have 64 here. Then we have to add another group size. So 64 plus 64 is equal to 128. Hence, our broadcast address is 172.99.184.128 minus 1. So our final answer is 172.99.184.127. Because again, we deducted 1 from 128. So the answer for number 8, our broadcast address again is 172.99.184.17. I forgot to highlight the answer to number 7. Let me just highlight them. Okay, highlighted. Let me just double check if all my answers are highlighted so it's easier. Then, for number 9, we are required for number 9 to solve for the binary format of our IP address. So our IP address is 205.36.72.56. So we just have to get the binary format. So again, we're using this table. I have already encoded the decimal per row. So again, we start 205 is greater than 128. So the answer here is 1. 205 minus 128 is equal to 77. 77 is greater than 64, so another 1. 77 minus 64 equals 13. 13 is less than 32, so it's a 0. 13 is also less than 16, so another 0. 13, however, is greater than 8, so the answer here is 1. Then 13 minus 8 is equal to 5. 5 is greater than 4, so another 1. Then 5 minus 4 is equal to 1. 1 is less than 2, so 0 here. And 1 is equal to 1, so the answer here is 1. Next, 36. 36 is less than 128, so 0. 36 is less than 64, so another 0. 36 this time is greater than 32, so it's a 1 here. Then 36 minus 32 is equal to 4. 4 is less than 16, so 0. 4 is less than 8, so another 0. However, 4 is equal to 4, so the answer here is 1. Then 4 minus 4 is equal to 0, meaning the remaining ones will be 0. Then we have 72. 72 again is less than 128, but 72 is greater, so 0. But 72 is greater than 64, so the answer here is 1. Then 72 minus 64 is equal to 8. So 8 is less than 32, so 0. 8 is less than 16, so another 0. However, 8 is equal to 8, so therefore the answer here is 1. Then 8 minus 8 is equal to 0, meaning the remaining will be 0. Then next is we have 56. 56 is less than 128, so 0 here. 56 again is less than 64, another 0 here. 56 is greater than 32, so the answer here is 1. 56 minus 32 is equal to 24. 24 is still greater than 16, so it's another 1. 24 minus 16 is 8. 8 is equal to 8, so another 1 here. 8 minus 8 is equal to 0, meaning the rest of this will be 0. Hence, our IP binary of our IP address is actually 1101.0010100010000.0010000.001111000. Let me double check. 4682468 24682468. Okay, so correct. Then, therefore, binary is 1100110100.00100.0100100. Then 0.001111000. So this is our final answer. Okay. Then, for our last item, finally, For our number 10, we are now required to look for the broadcast address. Okay. So for the broadcast address, again, we need to solve for the number of host bits. So 32 minus the prefix length is, let's check, is 29 here. 29. So minus 29 right here. So 32 minus 29 is equal to 3. Then 2, we need to solve. So hence, number of host bits is 3. Then we have to solve for the group size. 2 raised to 3. 2 raised to 3 is actually equal to 8. 0, 1, 2, 3, 8. Then, we need again the original IP address, which is 205.36.72.56. Then we need to keep on deriving network addresses until the fourth octet is greater than 56. So for our first network address, again, we just have to change the fourth octet. First, it's 0. So it is less than 56. So we need to derive the second. So 0 plus our group size, which is 8, is equal to 8. So the second IP network address is 205.36.72.8. It's still less than, so we have to derive another 1. So we need to add another 8. Our third network address is 205.36.72.16. Still less than 56, so another 1. Fourth network address, we had added another 8, is 205.36.72.24. Still, it's still less than 56, so another 1. So fifth network address this time is 205.36.72.32. Still, 32 is less than 56. So another 1. So our sixth network address is 205.36.72.40. Still, it's less than. So we have to create another 1. So therefore, seventh network address is 205.36.72.48. Still, it's less than. So we have to add another 1. So our 8th network address is 205.36.72.56, which is just equal. We have both 56. So we have to add another 1, and of course, it's gonna be our last one. So our 9th network address, 56 plus 8. So it's 205.36.72.64 because 56 plus 8 is 64. So we have to copy this one. Then, to solve, we have to minus 1 to the fourth octet. So, our broadcast address is 205.36.72.63. That is our broadcast address. So, I guess that's it for my course project. Finally, I'm done. And I will just be uploading this video according to the instructions here. And once again, I just would like to take this opportunity to thank Prof. Maridel. Prof, I know I have a lot of questions to you. I had like basically 2 tickets. Thank you so much for always entertaining me. It's very appreciated. You're really giving me timely feedback and clarifications. And I just want to say that I really like how you created our course modules because they're very easy to understand, they're comprehensive, they're concise. So again, thank you, Prof. And that's it for the end of this video. Thank you so much. May God bless us all.